This is Dynamics example 5.A.2. So in this problem we are asked to find why the car tends to nosedive when braking. So the first thing we're going to do is set up a free body diagram and a coordinate system. And as you can see, the weight force acts through the center of gravity in the negative y direction. And you're going to have two normal forces acting at each of the wheels, pointing in the positive y direction, and then two friction forces, one at each of the wheels, acting in the negative x direction. So next we're going to sum the forces in the x and y directions. So what we're going to get is the sum of the forces in the x equals the mass times the acceleration in the x. And when we do that, we get a negative force of friction at the rear minus the force of friction at the front, which will be equal to mass times the acceleration in the x direction. And we go to sum the forces in the y direction, we'll see that the acceleration in the y direction is actually 0. So then when we simplify it, we get the normal in the rear plus the normal in the front minus mass times gravity for the weight. We'll get that equal to 0. Now we're going to use Euler's second law, which states that the sum of the moments about g is equal to the mass moment of inertia about point g times the rigid body's angular acceleration. And since the rigid body does not have an angular acceleration, the sum of the moments about point g is equal to 0. And then we plug in the moments, we get that the normal force in the front times Bf minus the normal in the rear times Br minus the force of friction in the rear times D minus the force of friction in the front times D is equal to 0. And to relate these unknowns, we're going to have to come up with an expression for both the friction forces, which we get the force of friction in the rear is equal to mu sub k times the normal in the rear. And then we get the force of friction in the front to be equal to mu sub k times the normal in the front.
So now that we have all 5 equations that are needed, we can start plugging them into each other. And we start by plugging equations 4 and 5 into equation 3. Then, because of this, we get the normal force of the front wheel times Bf minus the normal force of the rear wheel times Br minus the coefficient of friction times the normal force of the rear wheel times D minus the coefficient of friction times the normal force of the front wheel times D equals 0. Now we can also recall from our second equation that the normal force of the front wheel is equal to mass times gravity, or weight force, minus the normal force. We can plug that into equation 3 to get Bf minus the weight force minus the normal force in the front wheel times Br minus the coefficient of friction times the weight force minus normal force in the front wheel times D minus the coefficient of friction times the normal force in the front wheel times D equals 0. And we can solve this equation for the normal force in the front wheel to get mass times gravity, or the weight force, times Br plus the coefficient of friction times D all over Bf plus Br. Now we can once again recall equation 2, where Nr equals the weight force minus Nf, so we can plug in what we got for Nf in the last equation to solve for Nr in this equation. So, to come to a conclusion, the car seems to nosedive because the normal force at the rear wheel is actually higher than the normal force at the front wheel.